start the afternoon today, and this time we have 3 talks, so we have to, be strong. Anyway, this is a pleasure to listen to Leandro Arosio. We're going to talk about polar spheres from strongly pseudo-convex experiments.
Thank you. So, let me start by thanking the organizers. And it's really a pleasure to be back at the actual conference with actual people. So, hope we can continue this way. And so we talk about the working collaboration with Matteo Fiacchi, Sebastian Godard, and Lorenzo Guerini. And so, horror spheres is the main topic. So let me just give some definitions about what horror spheres are. So there is a drawing which comes to mind when we are doing this. Then this is a classical horror cycle with vertex in this point here at the boundary, and okay, this exists also in the ball with a slightly different shape. In the ball, horror spheres are not balls, but usually ellipsoids due to the anisotropy of the metric in higher dimension. But still they are internally tangent to the ball. And there is a very simple formula. So it's the point which satisfies and so this object here is then called the horror sphere of center zeta. Zeta here is a point of the ball, and r is the radius. And of course, as the radius shrinks, as the radius goes to 0, the horror sphere shrinks to the vertex. Okay, so this is the object. They have a very simple geometric interpretation. Indeed, they are limits of Kobayashi balls whose center goes at the point and whose radius blows up in a switchable. Okay, so this is a possible geometric interpretation. And so now we know what they are, but why do we care? The reason is given by a beautiful result by Julia. Very useful, for example, in dynamics. So assume, I give the statement directly in the ball. Assume you have a self-map of the unit ball, which is holomorphic, and which has this the property that there exists. Assume that there exists a point. So assume there exists a point. Let's call it zeta, which has a finite dilation. What does that mean? Finite. Meaning that this limit as z goes to zeta of 1 minus z over 1 minus modulus of z. I want this to be not infinite. So when this happens, then something beautiful happens. Then there exists a unique point theta in boundary such that the image of the other sphere centered in zeta of radius r is contained in the first sphere centered in eta of radius lambda r. is an interesting relation between the Arosio center at the 2 points. And so we should think of this quantity as a sort of derivative of the boundary. Okay. And indeed, when this point here turns out to be equal to zeta, then it makes sense to talk about fixed points at the boundary, and this is very interesting dynamics. This is a little bit of motivation why this is interesting. And now, this was in the ball, and then of course it's natural to ask ourselves, can we do this in more general domains? So, first generalization is to do abate when the domain is strongly convex with C3 boundary. Okay, so how was this done? I think this was in the 90s. So the idea is noticing that in the ball, this object here can be defined also in an intrinsic way. So the points of the ball, such that the limit as W goes to zeta of G ZW minus DW0 is strictly smaller than the logarithm of R. So D here, I use it for the Kobayashi distance. So, as you see now, this is good because this is an intrinsic definition, so you can try to use it for more general domains. Only problem is that this assumes we need this limit to exist. Okay, so this is the problem. This is a trivial calculation, very easy. So in the board, this is not a big issue. But for example, for strongly convex domains, this is the fact that this limit exists is actually a theorem, of course, by Marco, and just a remark: there is no zero in strongly convex domain. There is no preferred point, so we need to take care of that. So let's define the Horace field with base point P. Center zeta and values r will be defined as the points such that the limit as value goes to zeta d zeta minus d w t is smaller than that. So now this Horace field depends, this definition depends on the base point chosen, but it is not a big deal. If you change the base point, you need just to change the radius. But the family of Horace spheres center at the point remains unchanged. So, Marco managed to prove that this limit actually exists, so this definition makes sense. And the proof is based on Leandro theory. And that's why it means strongly convex C3. It's just a brief sketch. One takes if you have a point Z0 in the domain, and you can define a function K, big K, capital K is a hyperbolic tangent of the Kobayashi distance from Z0. Is if the point is in D, and you define it to be equal to 1 day. And then Lambert proved that in these assumptions, this function is actually C1. Okay, so this was then used by Abate to show that this limit here, the limit of W zeta this can be written in terms of derivatives of these objects. So this is equal to the logarithm of the partial derivative of k p in the normal direction at zeta over the derivative again of kz in the normal direction again. Okay. So this was his proof. Of course, something to do here, and the rest on very big results of Lambert that this function is actually C1. Right? And that's why I need C3 and not just C2. So this is what was known about holospheres, and then you can, but still take a Julia lemma. It is exactly as the Julia lemma in the ball. You just need to generalize also the definition of the dilation because it was given in Euclidean terms. Then you define the dilation is just define it to be log of lambda is the limit as z goes to zeta of the distance from p to z minus the distance of p. Okay. Then you use this definition, and as a theorem, you obtain the Julia lemma exactly as before. So you have a function map which is holomorphic. Then assume that there exists a point zeta in the boundary of the domain, such that, let's say, with finite dilation, as here, finite dilation, and then there exists a unique point eta in the boundary, such that f of another sphere centered in zeta is contained in corresponding homosphere, same base point, and radius multiplied by the dilation. Okay, so this is what was known, and now the question is, okay, it remained open. The question that remained open is, can we do that in strong units? Okay, we don't have Lambert theory anymore. So we don't have this part here, we cannot use it. And so the whole strategy kind of breaks down.
Do you mind if only
I mean, it's all it's a theory developed about complex regularity of complex geodesics, and one of the existence of regularity of complex geodesics, and one of the important corollaries is that this function here is not complete. I don't know if it is the main point of the theory, but for this particular proof, the main point is that this function here is.
Strongly convex with respect to strictly convex is analytically some kind of.
Oh, strongly convex, I just mean that the boundary is moved, and the unit will take the Hessian, and it's not it's a positive definite, very classical notion, nothing. Okay, and so the question here is again, how do we prove that the limit that I wrote that was before exists? Okay, And also notice that such a limit does not exist for a general domain. For example, in the bidisk is a simple calculation, that limit will not exist. So we really need to use strong pseudo-convexity.
But other points where the limit exists in the case of the bidisk, this is what you're saying is that all the model is made of Guzman points. So do you mean there are no Guzman points in the bidisk, or there are some points?
That I'm not sure. I'm sure. What I'm sure is that if you take a point here, okay, that's what it's interesting. And so, what can we do in general? We reformulate the problem in another language using abstract compactification. I know that most of people here will be completely familiar with compactification, but since I need some terminology, let me recall very briefly. So we have a topologic space and a compactification is just an embedding, topological embedding, I in another topological space where this topological space is compact and the image is dense. This is completely trivial. Another thing which is still trivial but kind of interesting is that you have a sort of partial ordering among the compactification. So we say that the compactification is larger than another if there exists a continuous map phi, which goes from y1 to y2, which makes this diagram. So here we have the invariance, and here we have phi. Okay. And if phi is an homomorphism, we say that the two compactifications are equivalent. It's the same compactification, basically. And another thing which is trivial is that if y1 and y2 are alpha, and you have that y1 is larger than y2, and y2 is larger than y1, then actually okay, so this is just to orient ourselves in the world of compactification, because as we see in this conference, there are plenty. And we will need two of them. Unluckily, both introduced by Gromov, which creates a big problem in terminology. So the first one is for a function, boundary. Was introduced by Gromov in the 80s. So let me, it was already introduced yesterday by Carlson, but for those who were not here, we recall the definition. So we have this proper metric space. And you consider the space of continuous functions over it. You consider the convergence on compacts. And then you consider the quotient of the space with respect to the subspace of constant functions. Okay. And then you embed your x in this quotient, simply sending a point x is sent to the function dx, which is the distance function from the point x. Okay. So to every point in the manifold, in the metric space, we associate a function which is the distance from that point, and then we go to the quotient because we factor constants. So this is pretty simple, and then we just take the Horo function compactification and simply the closure of the image of this means is direct. Okay. So this is quite abstract, but it's also quite simple to understand what it means in concrete terms. The topology in this compactification, and this will be useful for us. So let me state it. So we take a base point D, and we take the sequence Wn in X. Then we say that this converges to a point in the Horo function boundary, which is represented. So a point is a class, the equivalence class of functions which just differ by a constant. So represented by a function h dimension p. Yeah.
So what's the Horo function boundary range?
The factor maybe I should have said function compactification. That is just the points that you add. Okay, the points that are in the closure that are not coming from the matrix space. Okay, and so you have this sequence Wn converges to this point zeta, represented by a function h which matches a p. If and only if something very familiar to us happens. But this conversion is really important. So you should recall this similarity now with what the limit that we were trying to h of x. Yeah. Right. So now we can remark one thing. Since this is the convergence here, we can remark that if we rephrase our problem, if the Euclidean compactification is bigger than the Horo function compactification, if I use this is larger than the Horo function compactification on B, then the limit that we are looking for, the limit exists. And so, of course, okay, so this is just very simple to see. So if you take this let's say morphism of compactification, and then you take a sequence converging to the point Z in the boundary, you apply the morphism here. You have that this converges to this image here. This now is in the Horo function compactification. Then you take H representing this point here, and you will obtain just that this function, this sequence here, the distance from x to Zn minus the distance from Zn to P converges to H of x, which is exactly what we wanted to do. So this image here exists. Okay. So this is what just rephrasing. Up to now, nothing. We didn't gain much. It's just a rephrasing of the problem. But now we can use some beautiful results and some other compactification to help us understanding what happens here. because it's a theorem.
Do you have an example where the different geometries?
Sorry?
Do you have an example where D bar is strictly bigger than D bar H?
I mean, we are going to prove that they are equivalent strongly to the complex. What we are going to do is for strongly to the complex there. So, but of course, in general, it can be.
I expect that the H to be bigger than D bar usually. I know that I don't know the certain comments.
They might actually not be comparable at all. Okay, so what I wanted to say, yes, we use now our second compactification, which helps us over here. Now this is the Gromov compactification, because our domains, the strongly pseudo-convex domains, are actually Gromov hyperbolic. There's a theorem by Gromov. So this is Gromov hyperbolic. And not only that, but which is very important to us, the Gromov compactification is equivalent to the Euclidean compactification. Okay. So this means that if we prove that the Gromov compactification is bigger than the Horo function compactification, we are done. Okay, because this is equivalent to the Gromov compactification. So if we prove that the Gromov compactification is bigger than the Horo sphere, the limit exists and Horo sphere exists. So we went to check what was known for as a relation between these two, and this is a theorem by Webster and Winchester. With 5, then you have that the Horo function compactification is larger than the Gromov compactification. This is always true. Okay, so unluckily for us, it was exactly the opposite inequality. Okay, and okay, let's not lose hope. There are actually counterexamples. So there are, this is actually true for a metric space, proper geodesic metric space. This is always true. And
here the hypothesis is
proper.
It's only true. It's
Proper metric geodesic space. Yeah. I maybe can do it, but we really deal with just proper metric, proper geodesic.
And the root ones or just
Sorry?
the root ones or about
No, can you repeat?
in the book here.
Yeah. Yeah. C2 boundary. When I write G is the domain, and when I write X is the proper geodetic metric space. And there is a counterexample, and by Webster and Winchester, you take this infinite ladder. Okay, and you have, let's say this is the point 0, minus 1, this is the point 0, 1. Then you see that the Gromov, let's call it this X, the Gromov boundary of this is a point. But the Horo function boundary is larger. Is the segment minus 1, 1. It's a simple calculation. Okay. And so maybe I should just briefly recall how you construct the Gromov boundary using geodesics, because we will need that too. This is very simple, so let me just briefly. So to construct the Gromov boundary, which when you add it to your metric space and you obtain the compactification, you take the set X of the basic rays. And you put an equivalence relation on rays. You say that a ray gamma is equivalent to a ray sigma if they stay about the distance. So if the distance of gamma t to sigma t is smaller than some constant c, as divided. Okay, and they are called asymptotic. These are called asymptotic.
Starting the same one.
Sorry?
So the starting one is the same.
No, rays. Just rays. Okay, but going parallel. Let's use it. And then you quotient of x, you quotient with respect to the relation. And this is one way of defining the Gromov. And so now you see now here, you see, for example, this is a geodetic ray, this is a geodetic ray, they stay at finite distance, so they go to the same point in the Gromov boundary. Okay. So, but what is the problem here for us? The problem here, and the reason why we obtain that the Borel function boundary is larger than the Gromov boundary, is that you have asymptotic rays which stay at non-zero distance. They never come together. So this is the obstruction for us. This is the problem that we want to avoid. So let me give a definition. So use this definition, say that two rays, gamma and sigma, are strongly asymptotic. I guess this notion already considered strongly asymptotic. If they come together, they're not just asymptotic, but they go closer and closer. And we can state this in two ways. We can state if the distance between gamma t and the ray sigma goes to zero, wave, or you can say, or equivalently, there exists two constants, and then if we reparameterize the rays, these are equivalent. This really means these two come together. And then, okay, so this is a simple notion, but then what's interesting for us is a notion on the metric space. And then we say that X, the metric space, has approaching universality. If asymptotic rays are actually strongly asymptotic. So, and this is far more common than one could think at the beginning. So this happens in complex analysis in the board. So this is true. X approaching the it's just a name to say that it's they come together. So this is true. So examples: the board, cap in -1 spaces, zero hyperbolic spaces, and also convex domains with the Hilbert metric when they are Gromov hyperbolic. So convex. which are Gromov hyperbolic. If they are not Gromov hyperbolic, it does not even make sense. Okay, so yeah, right. It's not interesting for us. No, you're right. You're right. So let me state the results. So we have the first result. So if X proper geodesic metric space, if X has approaching geodesic, then the Gromov boundary is larger than the Horner-Function boundary, and thus they are equivalent. Second, D bounded strongly pseudo-convex domain has approaching geodesics. And so I will try in the remaining minutes to give some ideas of the proof. So let's start with one. So we want to construct a morphism of compactification, which goes from the Gromov compactification to the Horner-Function compactification. So we need to start with rays, actually equivalent classes of rays, and associate a Horner-Function. And luckily, there is a notion for that. It's the Boltzmann function, so we take a gamma array and define the Boltzmann function. Limit as t goes to infinity of the distance x, the distance from x to gamma t, to y. And this exists because these are geodesic rays. And as you change the space from here, y, the Boltzmann function changes, but it just changes by a constant. So the class in the Horner-Function boundary does not change. So to gamma, you can associate this class of this Horner-Function, of this Boltzmann. And this is an object. But now, so this is called the Boltzmann map. So this is called B, this goes from Rx to but we want it to pass to the quotient.
Usually sometimes we take a set limit, which is there was the limit existed in this case.
Yeah, the limit exists.
What's your justification? Maybe it's just
this is
I know it's bounded, so I can take a subsequence. That's okay, but you can hear that as people who think it has a
yeah, this is the classical definition of a Horner-Function, of a Boltzmann function. Right?
Yeah, but sometimes you take there's a supremum or whatever to be sure that sometimes this does not converge.
No,
here, you're probably right, but I don't remember convergence in this case.
I should check. It seemed to me that it's increasing, but now I think it's increasing, but it's a calculation.
Okay, basically extension.
Yeah, it's not immediate, but not deep either. So it should be just.
Because you have to.
What is the argument of the notion? X or Y? Because you look at the
Oh.
options of what are those.
So here both, but then we realize that the dependence on y is not very interesting, but it just changes the by a constant, and then we consider it just as a function.
I consider it.
Yes.
Yeah.
But it's usually defined as a function of the two, because there is some reason.
No, but you see, am I seeing your compatibilization of functions of one.
And then, so we have this Boltzmann function, and we want it to pass to the quotient. Okay, so we want when we have two rays which are asymptotic, then they have associated the same Boltzmann function. Okay, and here we use our new concept, the approach to genetics. So, proof. So let's take two rays which are asymptotic, then we obtain as a gift that they are strongly asymptotic. Let me use this stronger symbol here. They are strongly asymptotic. So we know that there are these reparametrizations such that the mutual distance goes to 0, and then we do some adding and subtracting. Difference here. So the distance from x to gamma t minus the distance from gamma t to t, and then we subtract the same thing but with sigma s minus d sigma t s t. Okay, so this thing's not really useful, but it turns out that this is smaller. We do some triangular inequality distance, and this is smaller than the distance of gamma t plus capital T, sigma t plus capital S. We know that this goes to 0, and then we look at this. This converges to the Boltzmann function of gamma, and this converges to the Boltzmann function of sigma. And then they are the same. So now this was the proof of 1. Some minutes to give the idea of the proof of 2. And so the idea of the proof is
Stay bounded as you how you took the question by constant function. We could have taken the question by bounded function.
oh yeah.
And there's still that only if you are not.
Yes, but then it's not the same. It's not the same object. Okay, so we have this. We want to prove this. So we have two geodesic rays in a strongly pseudo-convex domain, and we assume that they are asymptotic but not strongly asymptotic. So how much time do I have left? So I can.
Oh, sorry. You've got 5 minutes.
Okay.
6 minutes.
6 minutes. Perfect. So just to let me give a bit sketch. We consider these two geodesic rays, gamma 1 and gamma 2, which are asymptotic, but but not strongly asymptotic. Okay. So, which means that there exists a sequence of times and two constants such that the distance of gamma 1 times n gamma 2 is bigger than little c, larger than little c, and this is of course smaller than the distance 2, which is smaller than c. So this means this is because they are equivalent, they are asymptotic rays, and this is because they are not strongly asymptotic. And then what we do here, we reparameterize these rays. Okay, so we consider reparameterization, gamma 1 of n and gamma 2 of n by changing also the domain. We just translate by j. Okay, gamma n of j of t is just gamma j of t plus n. Okay. So we now consider this sequence of reparameterized rays, and then we rescale by means of the squeezing function, because strongly pseudoconvex domains, it is known that the squeezing function goes to 1 at the boundary. Okay, so which means if we call gamma n 1 of 0, we call it Zn. We can rescale, so there exists a holomorphic injective map phi, which goes from our domain to the ball and sends that point again to the origin in such a way that the image contains some large ball where this radii equal to 1. Okay, so due to this theorem by Ben, Guan, and Zhang, we know that this object exists, and it allows to rescale and to pass to the limit. In the limit, we obtain that up to extracting subsequences, we obtain that these sequences converge to two geodesic lines. Okay, because it's immediate to see here that we have that the distance of gamma 2n 0 to Zn is smaller than capital C. So we know that there exists a convergence of C for both. So we have, we consider them. Let me just write what we do. We rescale like that. We extract, and then this converges to eta I, which is a geodesic line of the ball. Because in the limit, these images they take the whole ball. Okay, so the limit is the ball. So this converges to these two geodesic lines, and we're done because okay. So we have the first geodesic line is passes through the origin, but the second geodesic line calculates the distance to the origin is smaller than the first. So these two geodesic lines, one passes to the origin, the other one has same initial and final points, because you can calculate the supremum over R of the distance at the 1 t, at the 2 t, which is smaller than 2c, so they have the same starting point and point. They are different, so this is equal to
we have questions?
Yeah, I think there is Bas with a question. Bas, I think you can speak.
Yes. So nice talk. Thank you. I've looked at your paper too. So basically, some in metric geometry and the Hor function compactification, there's something developed actually to put a distance at the subset of the Hor boundary. And so you can actually put a distance there, which potentially might have infinite value. So, and this is called the detour distance, which was developed by Cormac, Walsh, and others. And this is a very useful thing. And I think in the setting where you're working, basically all the, so this Hor boundary, it partitions into these, well, if it's all Busemann points, which is in your case the case, all singletons. So lots of, I was wondering whether you've actually thought about applying this sort of detour distance. I think it makes sense in this context to actually show that you have this continuity and this fact that if you are actually strongly asymptotic, you are actually getting the same Busemann point. And if you stay weakly asymptotic, you still actually get the same Busemann point. That's the whole point. And that
I never thought of applying it for that, but I mean, the result that you mentioned, this is really just a very short calculation, so I don't think you need.
No, but it's just, I think it provides some context to some of the reasoning.
Probably.
I'm not saying it shortens the arguments, that's for sure.
Probably. I'm not an expert on this detour metric, but I'm sure it should be interesting to consider that. Yeah.
Yes. And then this sort of Julia lemma, did you ever think about looking at this in the context of, say, Hilbert geometries? I've actually never thought about it. In the context of Hilbert geometries, could one make sense of a sort of Julia lemma?
Oh yeah, so this what we did here, it's actually already known in the case that at least Andrew told me that the fact that it has approaching geodesics, the Hilbert geometry was already known, but without that name, of course, because the Julia lemma, because I didn't say that, but as a third result, we obtain a Julia lemma exactly as in the bowl with this notion, and this applies, of course, in the case of the Hilbert metric. But I never saw any mention of that, except in maybe some very old papers of the 50s on transactions. So it doesn't seem to be something that has been considered much. I also wondered why, but
yeah, maybe Bearden has done something on it. You might want to look at Bearden's work. Okay. He was quite keen.
Really about the Julia lemma and the Hilbert geometry?
Yeah.
Okay.
So yeah, I'm not sure. You might want to look. Well, thank you.
Yeah, thank you very much.
Yes, so I was wondering, is that true that like a strongly convex domain approaching the lens?
A strongly convex?
Yes.
Strongly convex is also strongly pseudo-convex.
Yeah, obviously. But then can you have like in
I would say that this is the proof.
No.
Yes. Huh?
You can be using complex geodesic and showing that we are
Yeah, but then you don't. Okay, because you can say that every geodesic is contained in a strongly in a complex geodesics, and maybe then you can say something. Yeah, because I mean in.
If you can do that, then do you still need the regularity at the boundary?
Yes.
No, but here you also have regularity at the boundary. In this theorem, it's strongly pseudo-convex layer C2.
Yeah, and you say that you value C3.
Yeah. So I mean, this theorem, this result actually lowers the regularity of a boundary. Yeah, this is correct. Yes. Actually, Marco, I think he said that you could probably with some effort generalize his methods to obtain sequence, but I don't know how. I mean, he said that.
And so I suppose strongly to my question, I suppose strongly to the convex is a natural limit for such result, because if you went to finite type, for instance, you would use the squeezing function.
Oh, yeah, that's a good question. We actually went to convex finite type.
Convex.
Yeah, I mean, for finite type, I think there is no hope at the moment, but they don't even know that it's not. But we managed to do the same thing with convex finite type, and replacing the squeezing function with scale. So, but the code is a little bit more complicated because here the model domain, once we scale the model domain is a whole. Very simple, very. In that case, it's a model domain. It's not that easy to understand. For example, that you couldn't have that genetic line set up. You don't know. So you need to work a little bit with complex geometrics instead and try to find.
Okay.